Okay, in this segment, we're going to be taking a look at a brief look at something which is basically a resistor in series with a nonlinear device. And hopefully this won't take too long. So we're going to consider having, say, a voltage source, a resistor, and some device, which we're not specifying, X connected up like this. And we're interested in there's some initial situation where we have Vn applied, and there's some In flowing through here. There's going to be obviously some drop across the resistor, which we could call V sub R. And there's some drop across the device X. We're going to assume that X is characterized incrementally by a parameter R sub X, which is the incremental resistance of X, which is basically delta Vx over delta Ix. I mean, formally it's the partial derivative, but it's going to be approximately equal to this, so that we have an incremental Ohm's law, where we have that delta V sub x is given by delta I sub x times this Rx. Okay? Now we're going to be interested in two things. First, we're going to be interested in if we increase Vn by some delta Vn, right, there'll be some increase in the current flow from In to In plus delta In. There will also be some increase in V sub R and some increase in V sub x. And we'd like to know, what is the relationship between delta Vn and delta In? So 1, what is the relationship between delta Vn and delta In? And 2, if we think of this as sort of like analogous to a two-way voltage divider, we've got some total voltage increase here, delta Vn, and some fraction of it is dropped across the resistor, and some fraction of it is dropped across this nonlinear device X. What is the fraction that's dropped across X? So what fraction of delta Vn is dropped across X? And so this gets at sort of what is the series combination of two incremental resistances look like. The incremental resistance of a linear resistor is just, of course, R. It's R everywhere, but it's also incrementally R. And this question gets at, is there something like an incremental voltage divider rule? Okay, so those are going to be our questions. And so what do we know? So I'm going to punt these questions for the time being. So we know KVL before the change. That tells us that Vn is equal to V sub R plus Vx. KVL after the change tells us that Vn plus delta Vn is equal to Vr plus delta Vr plus Vx plus delta Vx. And so if we subtract the before from the after, we get an incremental KVL, which says that delta Vn is equal to delta Vr plus delta Vx. So if we do after minus before, we get that. KCL basically tells us that the same current flows through these two devices because they're connected in series, and of course we can do the same thing, and it just tells us that delta IN is equal to delta IX. So KCL, incremental KCL, let's just call that incremental KCL for shorthand. Delta I in equals delta I R equals delta I X. Okay. So Ohm's law for the resistor let's just say Ohm's law before tells us that V sub R is equal to IN times R after the change tells us that VR plus delta VR is equal to IN plus delta IN times R. We can distribute the R and subtract before minus after, and we get basically that delta VR is equal to delta IN times R. Now that shouldn't be a real big surprise. If we have an incremental Ohm's law that holds for one of these nonlinear devices, we should have an incremental Ohm's law for a resistor that's very similar. It's just the same as Ohm's law, except with the changes. So what are we interested in finding? Well, we know for device X, so incremental Ohm's law for X, we said, told us that basically delta Vx is equal to delta IN times R sub X. And so we have the delta, or the incremental KVL expression, 1. We have the incremental Ohm's law for the resistor, and we have the incremental Ohm's law for device X. And if we take 2 and 3 and substitute them into KVL, what we find is that delta Vn is equal to, well, it's delta Vr, which is delta IN times R, so this is delta Vr, plus delta IN times Rx. This is, of course, delta Vx. And so we can factor out the common delta IN. If we like, we're interested in solving for the incremental input resistance, Rn, which is equal to delta Vn over delta In. We just move this delta In downstairs over here, and we just get that this is equal to R plus Rx. So the incremental resistance of this series combination is simply what we would expect, given what we said in the last segment about the incremental conductances combining in the same way we would expect, and the incremental current divider behaving in the same way we would expect. Here we have another situation where we might expect that the incremental resistance of a series combination is just the sum of the incremental resistances, and that is indeed here what we see. So that's cool. We can also go back and take this equation. Let's call this equation let's say four, and solve it for delta In. Delta In is equal to delta Vn divided by R plus R sub x. If we call that equation 5, if we take 5 and substitute it back into 3, which is our incremental Ohm's law, we can solve for delta Vx directly. So it's just Rx times delta In, which gives us Rx over R plus Rx times delta Vn. So this is our incremental voltage divider. So we have here the answer to our second question. Basically, the amount or the fraction of the input voltage change that is dropped across the second resistor here, the second incremental resistor, is just given by Rx over R plus Rx. And this is exactly the same form as our two-way resistive voltage divider. Okay, so this is behaving pretty much exactly like we would expect if we just think about what we've learned about linear circuit analysis, holding for now incremental analyses of circuits with nonlinear devices. Okay, so that's meant to be kind of a quick example that might be helpful. In the next segment, we're going to be starting on some concepts from semiconductor devices, and we're going to use that to get into the ideal diode equation to see where that comes from. And we'll start talking about transistors, which are specific types of nonlinear circuit elements, as opposed to these abstract clouds with an X in them. Anyway, we'll see you next time.